So the question is, if I have any mapping, how do I find the corresponding kernel? So sometimes you can really so if you think of the polynomial example, I could, I can write down the lengthy expression, which is of course computationally inefficient. And then the question is, how do you find the roots so as to write it in a compact fashion? But I don't think there's a general rule, because you don't know in advance. So you can check if you can find the roots, if you can write it as a polynomial kernel. But I don't think there's a general trick. So I think it's more the other way around, that people play with kernels of which they know that they are that they fulfill the Mercer condition, and then try and understand what mapping does that actually correspond to. And there are some rules which you will also see in your exercises, that some transformations of kernels keep the Mercer property alive. So this is how people typically go about. But then, for general data sets, those three that I wrote on the board is really what people mostly use. It's more when people have data other than just feature vectors, that they really try and construct kernels that are meaningful in that domain only, like kernels for images and strings and graphs and so on. Any other comments, questions? Okay. Microphone is on. Good. Then I want to talk about structured output prediction, and in particular the structured output SVM. But first I want to put that into perspective. So flat versus structured data. And we have implicitly always dealt with unstructured or flat data. So the typical setting would be that the input is, for instance, a feature vector. And the output would be a probability or a class membership. So essentially here we have a vector, and there we have a scalar. And that's it. And this is the setting that's used 95% of the time. So this is, if you have objects, you try to characterize them in terms of features, and you have a simple quantity that you try to predict, and that's all. And that has been hugely successful over the last 20 years, or even longer. However, beyond that, there is the structured input setting. Where the input can be structured, as the name says. So for instance, this could be a string of differing length, or it could be trees, or it could be graphs in general, or time series. Or images are a typical example of structured data. And if you want to use the standard setting, well, you would compute features that give you a constant dimensionality. So if you're looking at trees, you would look at features like what is the depth of the tree, how many nodes does it have, and so on. But you would not use the tree itself in the standard setting. In structured input setting, you really do use the tree itself. And for instance, this can be used in conjunction with support vector machines if you compute appropriate kernels. So for example, there are kernels that can compute the similarity between one tree and another. And then you would really do justice to the structured nature of your input. But the output in such cases is still just as above, for example, a class membership. And there's an even harder problem, which I want to talk about today, namely structured output, or more precisely, structured input, structured output prediction, where the input is structured and the output is structured. And so the input can be any of a string, tree, graph, and the output also. And I will start with an example that I will use as a running example throughout this hour. So what you see here are images of 3 different terrains, namely color-coded height maps. Okay, so we have 2 mountains here, and we have a mountain and a couple of valleys here, and 2 craters or 2 valleys there. And let's say that the task we want to solve is to predict where a human would walk. So let's say you want to construct a new campus, and you have the terrain, the topographic map, but you would like to know where are people going to walk? Where should you build your paths? Then for these 3 different terrains here, these are our training set. For these 3 terrains, there is the path that naturally evolved. So let's say that you had this terrain somewhere, and no path was built, and people just walked across. And people, on the one hand, they try to pick a short path from the upper left to the bottom right corner, but they also try to avoid climbing too many hills or going through too many valleys, because that would be strenuous. So the solutions indicated with the heart, those are the true outputs. And this is what I mean by structured output, structured input. The structured input would be the topographic map, and the structured output would be a path, which is more than just a scalar number, or more than, it is even more than, I can put this into a vector, but there are some constraints here, namely that this path is continuous, or that this path actually starts at the top left and ends at the bottom right corner. And these extra features are no longer visible if I just encode this path into a vector. So here are the proper solutions, the good solutions, and then you can think of millions of bad solutions. So here, for example, solutions where the path is very short. It's the direttissima, but it goes up and down a lot. Here, on the other hand, you have paths that are that totally avoid both the hills and the valleys, but they are very long. And we have other intermediate paths. And now, if you want to treat this as a learning problem, then you could, the naive way would be to treat this as a multiple class classification problem. So you could say, this is the good class, and this is one bad class, and this is another bad class, and this is another bad class, and so on. Now, since there is a near infinity of wrong paths, of wrong outputs, that is not feasible. And today I want to discuss a way out that is feasible under quite a number of constraints. And this way out is by means of structured output SVMs, or structSVM for short. Okay, and the first step in using such a structSVM is to again cast the problems into a space of a fixed dimensionality. So we have here a compatibility function, which in this particular case, for the example that I've used here, had just two features, namely the length of the path and its average steepness. But it will express the compatibility of any topographic map or any terrain with any path. And now in this specific example here, all the topographic maps happen to be of the same size. But that's not true in general. So you can have inputs which are of different size, sequences which are of different length. And by means of this similarity function or compatibility function, you map your input and your output. So you evaluate the compatibility of these two, but you also map them to a space of fixed dimensionality. So structured output SVMs, or structSVM for short. So we have a couple of ingredients here. Namely, some kind of structured input X, then a structured output Y, then a feature or compatibility function, which here was called psi. Going to use this notation, which is multivariate. And as the name implies, it measures the compatibility of a given input and a given output. Then we have the weight vector, which in conjunction with this compatibility function will allow me to compute a score. So a score f of x and y is given by this inner product of my weight and the compatibility function. We also need a loss function that tells me how similar a output y prime is to the desired or to the true output. And finally, we need a scheme to efficiently maximize this function. And the stress is on efficiently maximize, so that is not so easy to come by. Now, in learning, our task will be to find this weight vector W, and there have been or different strategies are being used to find this vector W. Namely, on the one hand, people use conditional random fields, or discriminative random fields. And they are parameterized so as to maximize the likelihood of our output given the input. And what we're going to look at today, the structSVM maximizes the margin in analogy to the normal SVM. Maximizes the margin between, well, the true and all of the false solutions. By another set of orders, a different method was proposed independently, namely maximum margin Markov networks. And they are really a special case, so they are also abbreviated as M3N, and they are really a special case of the structSVM, where the discriminant function can be decomposed over the cliques of a graph.
In this case, what are the true and false solutions? So where is this binary?
It is, you mean in this Walker example, in the topographic example that I showed?
For example, in the setting in general.
So you need a training set of inputs with the correct outputs. And you then start with some random weight vector, which will typically give you, when you then maximize for this initial set of weights, if you then maximize this score function, or if you find the y that maximizes the score, it will typically not be the correct y. And then you start tweaking your weight vector until you get the desired result.
But you have a label for each y if it's good or bad.
Yeah, I have a set, so my training set consists of inputs and then the true outputs associated with these. Okay, so in this example that I showed here, the training set would consist of these three topographic maps and then the true paths. So these true. On the other hand, there's an infinity of wrong paths, and these you cannot represent in the training set. So you let the algorithm itself come up with wrong examples, and well, if they are wrong, that tells you how to change your parameterization. Okay, and we can now derive this in formula that will remind you of the normal SVM that we've seen before. So I will minimize. I introduce a slack variable straight away now, so we're having a soft margin here. So far, it's identical to what we've seen. And now we have the following set of constraints, namely for all observations I and for all possible outputs. So this script y would be the set of all outputs. For example, in the application that I've shown here, it would be the set of all possible paths that start in the top left corner and end up in the top right corner and only proceed in a monotonous fashion. So you're not allowed to make detours or in this path. yi is the true solution. So let me annotate this. So this would be the true output for sample I. This would be the set of conceivable solutions, which is huge. So this one will comprise millions and millions of possible solutions. And for all of these, we request that the score difference between the true solution and the best false solution, or any false solution, is greater than the desired loss. So so what does this say? If I multiply my current weight vector with the compatibility function of the true solution, so these two will give me the score of the true solution. And if I multiply W with that one, it will give me the score of any other solution. And I request that the difference between these two scores should be at least as large as the loss that I have to define as a user. So how much do I need to pay if I predict the solution y instead of the true solution yi? And then this is just used to relax the constraint a little bit. These are the slack variables that we had also seen before. So this is the true solution that I would like to predict. This is any other solution. And I want to now tweak the weight vectors W such that the margin becomes as wide as possible, and at the same time guarantee that the score difference between the true solution and any other solution is larger than the cost that I should pay if I predict the wrong instead of the right solution. Okay, and we also have the condition that the slack variables should be larger than or equal to 0. Okay, now as before, we can set up a Lagrangian. And now comes this constraint. So we have this should hold for every sample I, and it should hold for every solution except the right one. And this difference vector in compatibility space, or the authors of the paper, Joachims and his colleagues, abbreviate by delta psi I of y. So the contents of this parentheses here are abbreviated as delta psi of y. Okay, then comes the second Lagrange multiplier for the second constraint. And now, by what we've seen in the last hour, we can now mechanistically go on and mechanically go on and differentiate this whole thing with respect to the weights, which will give me W minus and as always, we want to minimize with respect to W, so we set this to 0 and obtain an expression for W0 that is a little reminiscent of what we had seen before. And secondly, we differentiate with respect to psi. Which should also be 0. Okay, so we gain another condition, and we can insert these two into the Lagrangian, giving us our Wolfe dual. Okay, now all of that again can be written as W. So we have so I first replace C here. So this gives the plus the sum over I psi I times the sum over all the wrong solutions Okay, then as before, this could be written as W. It has been subtracted already from the plus 1/2 we had here. So we had plus 1/2 W transpose W minus W transpose W gives us that. And now we have to collect the remaining terms. Okay, and it is true that this holds for psi 0 because we have used this condition here, which only holds for psi 0. And there is an error here. There should be no psi. Okay. Now, let's see if anything drops out. So we have psi I times the sum over the alphas with a plus sign, and here we have the same with a negative sign. So this will cancel. And we have the psi and the mu with a positive and a negative sign. So that will also cancel. And we are left with the following maximization problem. And now insert again this expression for W0. Okay, and this is the last remaining term. And we have a couple of constraints. So we know that the Lagrange multipliers should be larger than or equal to 0. We also know that mu should be larger or equal to 0. And we have this condition on the cost. And these two we can summarize as saying that the sum over all the alpha I y must be less than or equal to c. Okay, so it looks similar to what we had before, except we have a couple more indices. And importantly, again, this score difference never walks alone, or this difference in compatibility space always appears in couples. and for this reason we can use the kernel trick again. By taking instead of this inner product, we can define any kernel function that fulfills the Mercer's condition. Okay, so far so good. Now the only problem is that this summation here, so we sum over all possible solutions except the right one. This can be an exponential number of terms. And the same holds for that one here. So this comes from the huge number of constraints. So this set of all conceivable solutions is huge. So what the constraint here says is that simply put, our algorithm after training should give a higher score to the true solution than to all the wrong solutions. And since there is a near infinite amount of wrong solutions, we have a near infinite set of constraints. So far, so bad. And this is why we resort to an approximation, namely two cutting planes. So here's a pictorial summary from Finley and Joachims. So really they used this slide. We have the quadratic minimization problem with no constraints, which would have its optimum here. And then we have a very large set of constraints. And now the idea is to well, start with some random initialization, for instance, of the weight vector, obtain a poor solution, realize that it's a poor solution, and introduce a constraint which will prohibit this particular solution. Okay, so this is our feasibility space. We want the most purplish color possible within this set here. So the set of feasible solutions, this is the optimum solution. And without constraints initially, okay, we go to this minimum, which is not feasible. We now identify a constraint that was violated by the solution. So this constraint here, and then given this constraint, solve again. And now given this constraint, so the current best solution would be this one. This is closest to the global optimum here. And because this is still outside the feasible region, we introduce another constraint, and given this constraint, find the best possible solution, which is currently here, and then keep iterating until we come to a point where further augmenting, well, until we have converged, so until we find no more constraints that will help us improve the solution to our problem. And in this, it's called cutting planes because, well, at least the first cut, it really eliminates a half space. It cuts away half a space. This is an approximation because we are going to use, we're going to introduce an error cutoff, so an amount of admissible error that we're willing to accept. Yeah, and because this will take some time, we should make a break here.